Good afternoon. It is a pleasure to me to deliver this kind of special post-Christmas lecture to an unknown public in India. And although I know Christmas is not a special holiday for you in India, I am a friend of Vivekananda. I was very fond of what he's writing, so I can understand that you may look at these times also as a period of holidays, and I chose a subject which may be appealing to a large number of mathematicians from various areas. You see, my title is Diophantine Equations That Moved Mathematics, and which is the most adequate equation in this context, if not Fermat's last theorem. You see it here, x to the n plus y to the n equals z to the n. Does this equation have integer solutions which are pairwise co-prime? And you can reduce it to the case when the exponents are prime. Because, of course, if you have a solution to this, then you can pick a prime divisor of n, and there is a solution also to the equation with prime exponents. And if you show that there are no solutions to the equations with odd prime exponents, you're pretty in good shape. Catalan is a slightly less known equation, but since I had some contribution to this solution, I decided to say some words about it too, especially because there are common patterns that arise up to some point in these two equations. So Catalan is an equation in two variables. You have 3 with Fermat, you have 2 in Catalan. It's x to the n minus y to the n 1. And actually that's an equation that is born in this very simple example. 9 minus 8 is 1. That's something that everybody who plays around with numbers might have discovered with some surprise in someday, namely that you have this difference of powers of numbers, the square of 3 and cube of 2, which are apart by 1 unit. And so the natural question is if this is an isolated phenomenon or if it occurs more often. That's a Catalan question. And here too you can concentrate on the case when the exponents are prime numbers. Now, just as a general remark concerning my talk, I am now here in our main conference room in the Institute of Mathematics of Göttingen. That is Hilbert's Institute of Mathematics. Unfortunately, you cannot see much of it, but what you may see during my talk is that we have 2 sets of 3 blackboards, and I switch from one to the other when one set is filled, and there may be some technical delays in all this procedure because it's an ad hoc organization. So if you see some incongruencies in my movements, it has to do with the technical background that I have to control by myself. There's not many people around in these days here in our institute. Okay, now back to our subject. The equation of Catalan has a history which starts in the 12th century, and the equation 3 to the n minus 2 to the n equals to 1 was of some interest because of Platonic harmony teaching. In the Platonic harmony teaching, the harmonic intervals were quints and octaves, and having harmonic intervals was related to this kind of equation. And it was proved already in the 13th century by a Jewish Spanish scientist, we would say today. He was a universal scientist. He was also a theologian and whatever people, astronomer. And he proved that the only solution is this one to this question. And there were also further intermediate discoveries. Euler contributed until in 1842, Catalan formulated this general question. And then we can also assume that P and Q are not two due to works which followed pretty soon after the formulation, for the case of Q by Victor Lebesgue, and for the case of P much later by Zhao Ke, a Chinese student of Mordel who taught in Xiamen, where I visited. So much for Catalan. Now Fermat is more important. So the first stage of the history starts with the reading of Diophantes, his recently rediscovered books by Fermat. So 3 volumes of the arithmetic of Diophantes were discovered again only in the 16th century and were translated by Bachelet in Latin, and Fermat read them. And there actually he found, this is interesting to say nevertheless, you know, this equation with exponent 2 leads to Pythagorean triples, the so-called Pythagorean triples, and you know that these are of the kind z is y squared plus v squared, and then you can say x is y squared minus v squared, and y is 2uv. So that is the general parametrized solution, but already in Diophantes, Fermat read a very nice proof of geometric insights for the fact that these are the only solutions. I think you know this proof. I don't have the time, unfortunately, to go in all details, but the point is that Fermat read this proof, and that kind of inspired him to wonder what happens when you replace a 2, which leads to infinitely many solutions, with an exponent larger than 2. And his spontaneous insight was that there would be no solutions for exponents larger than 2. And the page, the famous page where he wrote that he doesn't have the space to explain why this is so, is exactly the page in Diophantes, his work, where the Pythagorean triples are being dealt with. So it's clearly an echo of Diophantes, his work that produced the famous question of Fermat, which lasted for more than 3 centuries, as you well know. And the main topic of this talk will be to follow several historical steps of mathematics that were inspired by these questions. So the first step on both sides is just a historical step, let's say until 1800. That's how the question was raised by Fermat in the mid-1600s, and then the case P equals to 3 was solved, I think, by Euler, but maybe more people in the 17th century. And there are several approaches, but basically you can do it with congruences, you know, by showing 3 is, of course, an important number when you deal with the exponent 3, but there are also other congruences that you have to look to, and eventually showing that, if you have a solution in the integers, this must be a solution modulo any prime, and if you find some contradiction modulo some primes, then there is no solution. And that is how this case is solved. The case P equals 4 is more interesting because it was solved already by Fermat, and he introduced here a very natural method, but that became very fruitful along the time and received the name of infinite descent. The method of infinite descent originated with Fermat, and the idea is that assuming you have a solution to a slightly more general equation, he considered this equation, so z does not necessarily have to be endowed with the exponent 4, it's enough to be 2. Of course, z to the 4 is also the square root of z squared. So it's a generalization of the case n equals 4. And assuming you have a solution, again, a smart and intricate computation is not a straightaway result. It takes 2-3 pages to do some investigations which are connected with the insight taken from Diophantine, with Pythagorean triples, in order to deduce the existence of a further solution in which x, y, so if you have a solution for this equation, you have a solution x prime to the fourth plus y prime to the fourth equals z prime squared, and x prime is less than x, and so forth in absolute value. You see, so these are descending solutions, and for every solution you find a smaller solution, and of course, since you are in the realm of integer numbers, this process must stop somewhere with a contradiction. So that was the infinite descent, and then we're getting closer. We already reached 19th century. Let me erase these things so that we can stay in sync with the two equations. What is there to be said on this part of the board? Well, there was a result of Euler, of course, who considered this equation geometrically, and that was one of the first elliptic curves that were investigated with respect to integral points in a lot of detail by Euler before the general term of an elliptic curve was introduced. So that was happening a while before Catalan stated the assumption that except for this special case, there are no other consecutive powers of integers. Now, at this point, we arrive to a place where it's useful to consider the two equations in synchronicity, because what happens is that you are tempted to use some divisibility in both cases. There are expressions which are typically divisible. X plus p plus y to the p, if p is odd, is divisible by x plus y. So we have this factoring, which yields z to the p. And likewise, for Catalan, you have this factor and multiplied by x minus 1. And furthermore, if, okay, now these factors already carry some information, because I will write here lemma. It's a lemma that is probably due to Euler. It says that if x and y are co-prime, then x to the n plus y to the n over x plus y and x plus y are as good as co-prime. As good as co-prime means that if they have some factor, common factors, the common factors divide the exponent n. And this leads to a case distinction which happened already at the beginning of the 19th century in Fermat. The first case when P does not divide x plus y, x times y times z, is a case where these factors will be co-prime. And then you know that both well, I will erase this lemma. Please recall it, how we got it. I can give it to you as an exercise. It's a simple lemma. And it is something that you can propose to your students to prove that if x and y are two co-prime integers, none of them one, no, one can be equal to 1, then x to the n plus y to the n over x plus y is has a common factor with x plus y, which necessarily divides n, if at all. Common factor may be trivial. So when the two parts are co-prime, then the two factors must be individually p's powers. Whereas when p divides the factor, actually since they are co-prime, it will divide exactly one of the three unknowns. Then you have this thing. You have to divide by p too. And this will be a p's power, maybe s1. And as to x plus y, you have to multiply it with p to get a t1 to the p. And it will actually then be divisible by a large power of p. Okay. So here, well, here I will make a big jump in the future and tell you that an investigation similar to what happens here led to the result that actually x to the p over x minus 1 must be divisible by p. So it's just this second case which can occur in the Catalan equation, and so we get this simplified equation. It's called the result of Cassels in 1960. These two cases are called FL last theorem number 1, and the second case of Fermat's last theorem. Okay, and now we're going to start to do some mathematics. The first step, the first great contribution of the Fermat equation to mathematics was something that I will write now down, the investigation of cyclotomic fields. And that was the birth of algebraic number theory. So what's the point? The point is, if you take a piece root of unity, which means that a primitive piece root of unity is a root of this polynomial called the piece cyclotomic polynomial. You divide x to the p minus 1 by x minus 1. So it will have all the numbers whose piece power is 1, except for 1 itself. These are primitive piece roots of unity. In the complex plane, you will have things like 2pi times a multiple over p. Things like that. Now this, in modern notation, if you join this number to the rationals, you will have all polynomials in your piece root of unity which build a field. You can multiply them, you can divide them, and get the whole field, which is called the piece cyclotomic field. This piece cyclotomic field is endowed also with some automorphisms which are induced by sending zeta to a power which can be anything between 1 and p minus 1. Of course, when c is 1, you get the identity. Now, what's the interest of joining this piece of root of unity? It's very simple. The interest is that for the Catalan equation, you already have x to the p minus 1 over x minus 1 is the product of x minus zeta to the c from c is 1 to p minus 1. So you have your y to the k there, which factors completely in linear terms somehow. But these linear terms are not linear polynomials anymore. They are numbers. They are numbers in this cyclotomic field. Likewise, x to the p over x plus y in the first, which we knew that it's, so this is y to the q. That is Catalan. And for Fermat, this will be the product of x plus zeta to the cy. This is a y. And so this is the first case. And for the second case, I will write it down, and you will need to think for yourselves or wait for a moment for the explanation. So remember, you had s1 to the p, you have to divide by p, and this will be again a product of x plus zeta to the cy, but divided by 1 minus zeta to the c. So you have these factorizations in your cyclotomic field. And the product of these factors, again, is a power. So in addition, these factors are in a certain sense co-prime. So you may expect by theory of divisibility that they should be p's powers, respectively, q's powers. And this is what Lamé has done. By divisibility, he assumes that x plus zeta y is a piece power. So he didn't call this a cyclotomic field, but he did work with a piece root of unity, like in a field, like in joining the piece root of unity. That was correct. This way he had a proof of Fermat's last theorem. Unfortunately, this assumption was wrong. So the assumption that these factors are co-prime as numbers was wrong, because what happens here is that the integers do not have unique factorization. So that is where the birth of algebraic number theory happens, because Kumar came and, for instance, gave the example 6 is 2 times 3 is 1 plus square root of minus 5 times 1 minus square root of minus 5. And you see you have two factorizations of the same number. That phenomenon is very wide and leads to introducing ideals. You have unique factorization in ideals. It's not the place for me for making a whole lecture on algebraic number theory. If you do not know these things, it may be motivating for you to study it somewhere else. What I will say at this point is that it took 50 more years to investigate the whole theory of ideals, ideal groups, ideal class groups, and we know that there is unique factorization in prime ideals, not only in this p-cyclotomic field, but in any number field, so-called. Number fields are finite algebraic extensions of the rationals. So that is why Lamé was wrong, but this kind of factorization keeps its own interest. Let me define some more notions here which are useful for discussing what followed. One notion is the notion of ideal class group. And that is the following thing. Imagine here you have all your ideals of a given field. Now the ideals A in K is an ideal if for every x and y which are in the algebraic integers of K, you will have, and every A and B which are in your ideal, you will have AX plus BY is also in the ideal. So they are closed under linear combination over all the integers, not just inside the ideal. And ideals tend to be generated, so they can be generated by two elements in a number field. In other rings, you may need more generators. That's a cruel dimension. In number fields, it's enough to have two generators, but if an ideal is generated by a unique number, then it's called principal. It's a principal ideal. So the principal ideals are a subgroup of the ideals themselves. You take fractional ideals, you define quotients of ideals, and then you have a multiplicative group of ideals. Principal ideals are a subgroup defined by one, generated by one element. Ideals, all the ideals are generated by not more than two elements. And then you have this exact sequence. The principals embed injectively in the ideals, and you will have a quotient. This quotient is called the class group. The class group of your number field. The quotient of the ideals modulo the principal ideals. And it's a finite group. So if you take and it's a abelian group, every ideal raised to the exponent of this group must be a principal ideal. And this is something that has a large consequence for this kind of equation that we look at here. The fact that there is a way to annihilate, we talk about annihilating the ideal in the class group. You act on an ideal and get a principal ideal. A principal ideal is much nicer because it's generated by one number, so it's close to numbers. It's close up to something weird, which also happens in general number fields, and this is the next thing that I need to explain in this more general frame, namely units. So these are the invertible elements in the algebraic integers of K. In our case, just to make things simple, the algebraic integers of our cyclotomic field are simply the ring generated by the powers of the root of unity. Okay, so you take linear combination over Z of the roots of unity and you get all the integers. That's a very special form of the integers. So every field has a ring of integers. The integers, algebraic integers, have the property of being zeros of polynomials which have leading coefficient 1. Now, of course, not all integers are invertible. In the rational integers, only 1 and -1 are invertible. In fields, there's more of them. And knowing the units is very important. So now let me show you what some units in the p-cyclotomic field are. Let me start by showing that the p-cyclotomic field, the p-cyclotomic polynomial, forgive me, is nothing than the sum of the powers of x from 0 to p minus 1. If you divide x to the p minus 1 by x minus 1, that's what you get. And now if you plug in 1, you get 1 plus 1 plus 1, p times, which is p. So p is the value of the p-cyclotomic field at 1. So look here, we have a decomposition of p. So we have already an example of a prime that splits. Actually, it doesn't split, it ramifies, because these numbers, which look, of course, different as numbers, they are essentially equal in the following sense. for any A different from B and not, different coprime to P, 1 minus theta to the A over 1 minus theta to the B is invertible. Why? Because there is an A prime let me see if that's what I need. No, I want B times B prime to be congruent to A mod P. Mod P is operations mod P build a field, so I can invert B mod P and find an inverse, and then I can write here 1 minus theta to the B times B prime, which is A, over 1 minus theta to the B. And then I apply to this expression the geometric series, and this is 1 plus zeta to the B prime plus zeta to the B prime times B minus 1. And this is obviously an integer. So indeed, this number is invertible. Okay. Now, these things which I will write like this, you take all possible quotient of the type 1 minus theta to the A over 1 minus theta to the B, and over them all the possible products and with possible repetition, then you get something which are called cyclotomic units, and they are almost all the units of your field, and they play a very important role in this context. And the last notion that I have to introduce is group ring and its actions. The group ring that we will consider here is, remember, we have a Galois group that I exposed above, the automorphisms of the P cyclotomic field, and the group ring over this Galois group is the set of elements theta, which can be written as the sum of some integers times the the automorphics sigma c. So the NC's are integer. These are formal sums, but since the automorphisms build a group, you can multiply them, these formal sums, and multiplication of automorphisms will simply be composition. Actually, the automorphisms build a cyclic group, so it's a very nice kind of composition. And now, this group ring acts, for instance, on, for instance, units. So if I have a unit, then theta acts on it by, so you take this theta, divide here. The effect of the action will be the product of automorphisms acting on the NC power of epsilon. You see, so in other words, the exponential notation means that some number or some ideal or some ideal class raised to sigma, to an automorphism, is precisely the result of the action of that automorphism on that particular object. So group rings act, and now we get a little bit more abstract. We consider an element of the class group. As I said, the group ring can act on that too. And well, there are specific, there is a module which I'll call S in Z of G, such that theta A is the principal class. The class of the principal ideals is the element 1 in the class group. And this holds for all A in the class group and for all elements in my ideal A, which is a Stickelberger ideal. And this is, you know, a very practical property for getting numbers out of ideals. Ideals are less easy to operate with. Numbers are more practical. And we shall see this as work as soon as I can switch blackboards. This is a problem that I solved now. Okay, so now you have learned a lot of things which were the theory developed from Kumar's insight. Let me, before I go further, mention a major result of Kumar. If P does not divide the class number of the P cyclotomic field, the class number is the size of the class group, then Fermat is true. So you see, suddenly exactly the things which Lamé expected not to exist, the class group, Lamé started from the hypothesis the class group is 1. And indeed, Kumar, 2 decades later, did prove that if that thing is true, then indeed Lamé was right. Then Fermat's last theorem is correct, but that is not a fact anymore. It is an assumption, and actually this assumption is true for roughly half of the primes, but we have no proof even that it would be true for infinitely many primes, even today. So now let me show you some techniques. What you do is you introduce some so-called characteristic numbers. I told you that x plus zeta y is a divisor of x to the p plus y to the p. Maybe I have to divide by p in the second case, so e will be 0 in the first case and 1 in the second case. And I define these numbers which are actually integral, even if you have to divide. And then you define this ideal. And to make a long story short, A to the P is principal, and in fact it's a principal idea A. So that is the entry into applications of cyclotomic fields and class group manipulations. The existence of this characteristic number and characteristic ideal. And now what you do is you take, for instance, for reasons that I can just sketch very quickly, let me write it down first and then explain. When you take an ideal in the Stickelberger ideal that I mentioned before, that will produce out of A a principal ideal, and out of A bar also a principal ideal, beta and beta bar. And this will be piece powers. Let's write it like this. Okay. So this will be principal ideals, and if I raise it to the power p, I got alpha over alpha bar. Remember, alpha a to the p is alpha. It's written here. Now, I have an equality between two principal ideals. And here is a trick with the units, and that is why you divide by complex conjugates, since with some quotient, additional quotient, there may be a root of unity coming in between, but if you fix that root of unity properly, you will get here an equality between principal ideals. And one of them is a piece power. And this, the fact that this right-hand side is a piece power, whereas alpha, remember, this is x plus zeta y over x plus zeta bar y may be times a, something which is nothing else than some root of unity in the case of second Fermat. So this is a simple expression that depends on the solution itself, whereas this is a piece power. And that is what Kumar has done, compare these two things and draw some consequences about the impossibility of Fermat to hold in certain cases. And in the case of Catalan, you have something similar. So over to Catalan, you have as characteristic number x minus theta over 1 minus theta, and you will have alpha prime over alpha prime bar to the theta, again for some element of this class group ring, is beta over beta to the q this time. And in fact, for the proof of Catalan, one does a step more, one does use other kind of annihilation in terms of real numbers, and then you do some power series expansions of this beta over beta bar. This is a novel approach, and so in both cases, you have beta over beta bar is alpha over alpha bar at theta over something, where something is p or q. It's p in the case of Fermat, and it's q in the case of Catalan. This is this point, is this point. And you have a power series development. And this thing can lead even to some contradictions in the case of Catalan, and it leads to some bounds. Now you will receive from me, by the time you have this lecture online, you will receive a paper of mine which will appear soon that uses this kind of approach of power series development in order to get some lower bounds in the second case of the Fermat last theorem. This is not such a lucky and interesting result because, as you well know, 1993 to 95, Wiles and then Taylor plus Wiles have proved Taniyama Shimura, which then implied both cases of Fermat's last theorem. So Fermat's last theorem is known to hold, as Catalan is known to hold too. Actually, that is then the third major historical step from Kumar to 1980s, actually. There was a rich number of results on the Fermat last theorem using tricks involving class field theory. So class numbers, properties of class groups, some algebra, and the conditions that arose, especially for the first case of Fermat's last theorem, the conditions that arose were more and more incredible, but never a final condition. That is why when Frey, and actually had Guarch before, had the idea to do this. You assume a solution to a Fermat equation with unknowns a, b, c, a to the p plus b to the p plus c to the p is equal to c to the p. And you take the solution and plug it into the equation of an elliptic curve. Well, it turns out that the elliptic curve will have a discriminant. The discriminant of an elliptic curve is a discriminant of this cubic polynomial here. So the discriminant will be a to the p times b to the p times c to the p over something like 32, I'm not certain, over a power of 2. And this power of 2 is weird. And actually, it's because of this power of 2 that the Taniyama-Shimura theorem, the modularity of elliptic curves, together with a descent from this curve and its modular function to one which has only level 2, all this implied that there is no solution to Fermat. So you see, you had a whole theory on elliptic curves, a deep theory on elliptic curves, which shows that this curve cannot exist. You see, you can write it down, but it cannot exist because it has arithmetic properties that are contradictory. So that was probably the last step, the last offer of Fermat to the development of mathematics. Well, yes and no, because, you know, Mochizuki let me write here So you may have heard that Mochizuki developed a theory called interuniversal Teichmüller theory, which he claimed that it you can deduce from it, among others, the ABC conjecture. ABC conjecture is something of this kind. People who are more cautious actually talk about ABC inequality. What is an ABC inequality? You write an equality between positive integers, a plus b is equal to c. And the ABC inequality will tell you that c is less than the radical of a times b times c. And you may have here an exponent and here a constant. And for various exponents, various constants, you have various ABC inequalities. But that's the essential message of the ABC conjecture. And the radical of a number is the product of the primes dividing it. So you remove the powers. So imagine if you apply this to FLT, you will remove the exponent p. Well, what is recent is that in December 2020, Mochizuki and 4 other authors have submitted a paper where an effective inequality was proved. The proof is based on the theory of Mochizuki. By the way, that theory of Mochizuki raised very many discussions, but now it is settled in the sense that it was accepted for publication in a very famous Japanese journal, and this fact is also communicated in Europe and in America. So eventually, already more than 12 people are specialized in the ideas of Mochizuki, and it is to be expected that slowly the waves will calm down and insights in this theory will spread in the community. And this is a very interesting application, because this new result not only says you can deduce the ABC conjecture from the interuniversal Teichmüller theory, but it gives you an effective ABC bound. And you see how hard it is by the fact that this constant that you see here is not just 721, it's e to the 10 to the 31. It's a very large constant. It would be a wonder indeed if you could immediately, and you also have an exponent 3 here, so it's not so simple, but it is an effective ABC conjecture. And now, to close the story, this may be to the latest +1 contribution of Fermat to the development of mathematics. Although Mochizuki was, God knows what his ideas, what led his ideas for the development of interuniversal Teichmüller theory, but there is this interesting application to Fermat too from this even more important result that happens after 25 years after Taniyama Shimura, which was a product of the Langlands program. This is independent of the Langlands program. And now my small contribution in this context is that due to this large exponent, it was not possible to prove the second case of Fermat using this inequality, although it's a good application. And I came with an improvement of the lower bounds for solutions of Fermat in the second case, which is almost large enough to allow a proof with this inequality. There's still something missing, but that's another story. Anyhow, it is this paper that I will attach to my talk. I've gone it now 3 minutes over time. I apologize for this, but I thank you for the opportunity to discuss this whole Christmas story of mathematics. And I wish you, I wish nice discussions, because in fact we will have 15 minutes of discussions after that. Bye-bye.